Hello, my name is Shane, and this is my data structure videos going over the linked list data structure. There are a couple prerequisites to this video. The first one is a knowledge of stacks and our queues. Though it's not entirely detrimental to this specific data structure, it is very helpful to have a knowledge of a data structure on hand. The previous video before that I recorded is over stacks, so I just invite you guys to check that out. The other requisites are, of course, a basic understanding of Python and other programming language, a knowledge of working with classes in Python, and then, of course, big O notation. So what is a linked list? Well, a linked list is a data structure like an array, except each element in a linked list is not contiguous with memory, and as a result stores pointers to the next element's address. Each element is called a node and normally stores a value as well as a pointer, indicating either where the next node is and or what node came before it. There are three types of linked lists, but in this lesson we will only be covering singly and doubly linked lists. Singly versus doubly linked lists are the types of linked lists we're going to be going over today. A singly linked list is a linked list with only pointers going to the next node. So we've got these objects and we're going to connect them by these arrows. And each arrow is a pointer to the next node in the linked list. Now, a doubly linked list also includes pointers going to the previous node. So if we just draw a bunch of back arrows right here, like this. In the grand scheme of things, doubly linked lists are far more popular, but both are applicable and fairly easy to use. So you're probably asking yourself, what is the purpose of a linked list? You're probably wondering, well, an array is super easy. It does the same exact thing. It stores data. You don't need pointers. Everything's right next to each other. And that's actually the purpose of a linked list. So when you're working with memory-sensitive projects, linked lists can provide extra flexibility when it comes to storing sets of data. So when working with arrays, in our case, a Python list, for the sake of preventing confusion, I will refer to a Python list as an array. When you're looking to insert a new element in an array, it can be quite pricey because you have to create room for the new item to do that. Elements must be shifted. So let's draw an array real quick. So got my brackets. This is item, 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 item. They're not zeros, they're just circles. And let's just say I want to insert a new circle at the beginning. So what I'm going to have to do is I'm going to have to shift every single item to the right to make room for this. And when it comes to big O efficiency, this is ON, simply because you have to move every single item of the list. Now, when it comes to a linked list, it's really easy because a linked list gives you the option to simply just add a connector. So like, let's just say I've got this linked list right here. This is my head right here, and this is my tail. Well, let's say I want to insert a new node at the beginning of my linked list. Well, I actually don't have to move everything over because in the grand scheme of things, I'm actually, let's just, instead of it being in this box, we're going to have a circle here, a circle here, a circle here, a circle here, a circle here. This is probably a better visualization for a linked list. So in memory, we don't know the exact location of each of the items in a linked list. We have their hexadecimal address, which is good, and it actually saves significantly more memory than it would if we had them right next to each other in an array. So I've got this pointer and it goes over to here. This is the next item, this is the next item, this is the next item, this is the next item. And each of them all have their unique hexadecimal addresses. And they have pointers going to the next item in the list. Well, let's just say I want it to add a new node at the head of my linked list. So this is my head right here. Well, I'm going to have, we'll just say that the head that we're wanting to add, this new node, is right here. I'm going to put a smiley face on it. Well, all we need to do is we need to add a new pointer to this and then just assign this as the new head right here. We can do the same thing for the tail. So it's significantly easier to insert and pop out items when in reality arrays are a little bit more pricey and time sensitive. So when it comes to the linked list data structure, it's not supported in Python as an automatic data structure. Like, for example, when we're wanting to create an array in Python, you have your variable name and you have it equal to an opening and a closing brackets, which you can add stuff in the opening and closing brackets ahead of time if you want to preset some variables inside your array. Linked lists don't work like that. You have to create them yourself. So the structure format is as follows, line 1 to line 13. Now on lines 3 to lines 8 is our node class, and I'll explain that in a second, but let's just look at our linked list class. So lines 1, 10 through 13. So the first thing that we have defined in our linked list is, of course, our initializer, and we want to initialize 3 variables, self.head, self.tail, and self.size. These are important because a linked list always has a head and a tail, and it's always a good rule of thumb to keep track of the size. Inside of our linked list class, we also have the node class, which we initialize 3 variables as well. Inside of the argument for the initializer, we of course have self and then the variable called data. The 3 attributes that are initialized when the node class is called is data, prev, and next. This specific structure is for a doubly linked list. If you wanted to write a singly linked list, you would just ignore the .prev, and you would just keep .next and .data. But this is a doubly linked list, so the .prev and .next are going to store the address location of the previous and next nodes in the linked list. Okay, so you're probably wondering, what can I do with a linked list? What are the different operators that we have? In the previous video when we talked about stacks, I talked about 4 main operators with a stack. Linked lists have 7 main ones, and of course there's other little ones that are more niche, but when it comes to the main operators, there are 7 of them, and I want to go over them with you. We have the insert head, insert tail, get size, insert node, remove head, remove tail, remove node, is empty. So those are the 7, and I have 3 fun ones at the bottom. But we're going to first go over the insert head. I do want to correct myself. There are 8 operators, not 7. This is what the insert head operator looks like. It has 2 arguments. It is self and data. Self is going to be an argument in every single one of your methods that you're defining inside of your linked list class. It just ties it back to the parent class when you use it. And data is going to be the data that's going to be stored in the new node. So on the second line, we have to create a new node. We store it into a variable named new_node. We then check on the 4th line to see if there's already a head in the linked list. If there is, the code will continue, but if there isn't, that also means that there's not a tail, which you now can store the new node as your linked list's head and tail. That's really important to note. You'll never ever have an instance where you have a head of a linked list but no tail, or a tail of a linked list and no head. If you set up your linked list structure properly, then you will never ever run into that issue. If there is already a head in place, you first are having the new node's next attribute equal the address of the linked list's head. So what we're seeing right here is new node.next equals self.head. This is really important because it's the first step in defining a head. Self.head will never have a previous value. And that's really important because if it did, then it wouldn't be a head. Now we need to have the linked list's head's previous address equal to the new node. So I just broke a rule that I already said not to break. This is important because we're wanting to make the new node the head. So when we do self.head.prev equals new node, we're just setting the previous address of the head to new node. And then we're going to fix that by saying self.head equals new node. In regards to efficiency, this operator yields big O1 efficiency. This is because you simply are adjusting the pointers of 2 nodes which will happen almost instantaneously. There's no parsing or anything like that. Following your insert head function, write the following code. The code is very similar to the insert head operator. We of course create a new node and check if a head exists. If not, the first, like after the else statement, stores the new node's address into the tail's next attribute. The new node then stores the tail's address into its previous attribute. Lastly, the tail attribute of the linked list stores the new node as its value. So again, we're just flip-flopping things around, just like the insert head. In regards to efficiency, this operator also yields big O1 efficiency. Just like the head operator, you're just simply adjusting pointers between the two nodes, which takes an extremely short amount of time. The size of the linked list. It is good practice to have the size of the linked list be stored as an attribute for future calling. So when we looked up here in the initializer attributes, we have self.size. We have it set to 0. And of course, when we look at insert head at the bottom, self.size plus equals 1, and the same is for insert tail. We can implement this by writing the following code. The single line return statement will allow us to get the size of our linked list at any time. If we did not implement the counting in our functions and did not keep track of the size, finding the size would yield big O n efficiency. But because we went ahead and kept track as we went, getting the size now yields big O1 efficiency. It's a huge improvement. It's important to note that you could just call self.size whenever you're wanting to use the size value and other methods you define. But when it comes to abstraction and keeping things private and protected attributes, you want to make sure that you're using getter and setter methods. It's more up to pure preference, but I personally like it. I know what you're thinking. This code looks super long and confusing. Don't worry about it. It's totally okay. This is the insert node function. You might want to insert a node at a specific index in your linked list. To implement that, it's kind of tough because of a lot of reasons, but we're going to go through it. And I know a lot's going on here, so let's break it down. There's a new argument in the function, and it's called index. This argument is for the user to submit where in the linked list they want the new node to go. The index argument is like a normal array where the list starts at 0 instead of 1. So if you have a list size of, let's just say 7, we go 0, 1, 2, 3, 4, 5, 6, and that's it. Same thing for here. Next we have an if statement followed by two elif statements and an else. We of course, before that, create our new node, get the size because we're going to be using the size. The if statement checks if the index is 0, meaning the user wanted to insert the new node at the beginning of the list. Instead of rewriting code, we can just call the insert head function. So for example, if index equals 0, linked list.insert head, self, and data. Just like that. Super easy, code's done. The first elif statement is checking if the index is equivalent to the list size. If the list size is 5, that means the largest index would be 4. If the index is equivalent to the list size, we can save ourselves some time and just call the insert tail function. So elif index equals size, linked list.insert tail self data. The second elif statement takes in account for an index argument that exceeds the current capacity of the linked list or is a number less than 0. For example, let's say the current size of the linked list is 5, meaning the largest index possible is 5, of course, to insert the tail. If the user inputted 8, it would be impossible to insert a node outside of the tail unless we were, of course, adding a new tail. The last elif statement checks for that and prints a statement to the user if the index argument is not in range of the linked list and to enter a number between 0 and the size of the linked list minus 1. I have this statement right here and it's outside of the screen. There you go. Now on to the meat of the function. Let me scroll down a little bit so we can get to this else statement right here. This is the rest of the code. We have our traditional check if there's a head function. If that doesn't pass, we start checking where the index is in relation to the beginning and the end. An easy out would be to parse through the linked list from start to finish, but to conserve efficiency, we give the method two options. If the index is closer to the end, start from the tail and work our way back. This is done by doing if size minus 1 minus the index is less than the index. So essentially what we're saying, like, let's just say that the size is 10. There's 10 nodes in our linked list. So 10 minus 1, meaning the largest index is 9. And let's say we want to insert the index as the third index. Go 9 minus 3. Actually, let's do it a little bit. Let's just say the index is 7. So we go 9 minus 7. If 2, so that answer, if 2 is less than 7, which is the index example that we just used, then we do current node equals self.tail, count equals size minus 1, so 10 minus 1, so it's 9. While count doesn't equal index, current node equals current node dot previous, count minus equal 1. So we're working our way backwards. If the index is closer to the head or equal distance from either the head or the tail, we start from the head and work our way forwards, just like this. The performance on a small scale is not noticeable, but this adjustment to the code is important when working with extremely large linked lists. Lastly, we simply move node addresses around until the new node is at the index. Essentially, we copy the new node's previous address to the current node's previous address. And after that, we copy the current node's address to the new node's next address. Then we store the new node's address as the current node's previous next address, as the current node's previous address. I know that's confusing, but so I'll try to break it down a little bit more. We've got our new node. Let's just say that we're wanting to insert it at index number 3. Well, index number 3, that's the current node. We're going to say new node dot previous is equal to current node dot previous. So we're going to store index number 2's node as the previous value for the new node. So we're not removing anything yet. Now we've got new node dot next, and we want it equal to the current node. So now our new node has index number 2 and index number 3 as its previous and next. So the new node's all set to go. It's connected. But now we need to disconnect the previous node and current node. So what we do is we go current node dot previous dot next. So it's going to be pulling the previous node next, and we have that address as the new node. So we've disconnected the previous node from the current node, and we've stored that new address into the new node, or as the new node. Now we do current node dot previous equals new node. And what this is doing for us is it's taking that current node, so what was index 3, and just changing the previous from index 2 to now our new node. And of course we add +1 to the size at the bottom. So essentially we're just copying addresses and flipping things around. In regards to efficiency, this method has O to the n efficiency, but is way more efficient than a traditional ON because we cut the parsing in half by the index distance calculation. Remember, we pretty much decide, okay, like which path is going to be quicker for us. And it's at least 2 times more efficient than parsing through the entirety of the linked list. Removing the head. Let's say you want to remove the head of the linked list. When working with an array, we could easily write array.pop and then 0 as the argument, which would remove the first object in the array and move everything to the left to adjust to the newfound space. It isn't so easy with linked lists, but that's actually a good thing. Let's check out the following code. In the array example, we can't use a single line to remove the head. Much like the other methods we are defining, we need to move around the addresses of the nodes. We first set the head to the next node after the head. So we're doing self.head is equal to self.head.next. After, we use the new head's previous address to continue to work with the old head. We use .prev.next to get access to the previous head's next address and set that to none. We then set the previous address to none for the head. Thankfully, Python garbage collection happens automatically and the head node is removed from memory. One last housekeeping item, don't forget to subtract 1 from the linked list size. If you forget to do this, other methods we will be defining will not work as expected. In regards to efficiency, this method yields big O1 efficiency because you are just adjusting the pointers near the head and removing the old head. Removing the tail. Much like removing the head, we can also remove the tail. Let's check out the following code. If you said that this looks just like the remove head code, you'd be correct. We're essentially taking the remove head code and reversing the address assignments. Instead of having self.head equal to self.head.next, we're having self.tail equal to self.tail.prev. Everything else follows opposite. And don't forget to subtract 1 from the size. Just like the remove head method, the remove tail method yields big O1 efficiency because you are adjusting pointers near the tail and removing the old tail. Removing a specific node. You may want to remove a specific node. You can easily do this if you know the index of the node you are wanting to remove. So let's check out the following code. Much like inserting a node at a specific index, removing a node from a specific index also yields big O n efficiency. Instead of having to parse through the entirety of a linked list, I implemented the same math to determine the distance to the index to find the most efficient path. Either from the head or the tail, which should at least increase by efficiency 2 times. So when we look at this, this is like pretty much the same exact thing, but except the last 5 lines are really the difference maker. We have current node.previous.next, so the previous node's next value is equal to current node.next. And then we go current node.next.previous, so the next node's previous address is equal to current node.previous. And then we do current node.next and current node.previous equal to none. And then the Python garbage collection, and I just realized I explained that without it being scrolled down. The Python garbage collection is going to take care of this and it's going to get rid of it. An important thing to note too up here is instead of the insert head or insert tail, we're doing remove head and remove tail. Remember, it's the same exact thing as the, but of course we have a little adjustment here, size -1. That's going to give us the index of the tail, and we're just removing it and storing everything back into it. The last operator that we're going to be going over is if the linked list is empty. And that's really just returning a Boolean value. So we'll pull the self.size. If self.size is equal to 0, return true, else return false. If we wanted to, keep protections, we can go if linked list dot get size. We could do that too. It does the same exact thing. This one just helps with, like I said, the abstraction a little bit and protection of linked list attributes. Now, I do want to go over one quick thing before we get into the problems that you can solve with the linked list and some of the other semantic things. This is a function I created by myself. It's called display structure. It doesn't take any arguments, of course, except the self. We have a variable equal to a empty string called structure. We have current node equal to self.head, and of course size is equal to size. So we go for I in range size, of course it's going to go from 0 to size minus 1. If I is equal to 0, what we're going to do is we're going to do structure plus equals, so we're adding a string to it. The data that's inside the current node, and the space in this little arrow in another space. If I is equal to size minus 1, meaning it's that last index, it's going to be this backtick arrow, space, and the data. And of course, if it's any other thing, we're going to have back arrow, space, data, space, front arrow. And then of course at the bottom, it's going to go current node equals current node.next. This is really useful when you're wanting to get a visualization of your data. It's going to return the structure so you can print it out. I'm going to scroll down so you guys can see the printed out version below. So I have, of course, created an instance of the linked list, and I've inserted 5 nodes. They have the letters A, B, C, D, and E. And then, of course, I've printed out the .display structure. When we look down here, let me scroll down a little bit. We see A, pointer, B, which has a back pointer to A, and a pointer to C. C has a back pointer to B, and a pointer to D, and E. So that's the visualization. This is just more something that I wanted to do. When I was working with debugging, it's helpful, just so if you want to keep track of what your linked list is looking like. So what problems can be solved with linked lists? The main problem that comes to mind is the problem of memory conservation. When working with arrays, you tend to be confined to a block of memory where each item is directly next to the item before it. On a small scale, it's fine, but as you expand with projects, linked lists provide the flexibility of having comparatively less memory than traditional arrays. Nodes within linked lists have pointers that point to the hexadecimal address of the next node in the list. And if the linked list is a doubly linked list, the node will also have a pointer to the hexadecimal address of the previous node in the list. Linked lists also have significantly faster insertion and deletion than a traditional array. If you want to insert an object at the beginning of an array, you have to make space for that new object by moving each object in the array to the right, which takes O to the n time. When inserting or deleting into the beginning of a linked list, you simply assign a new address in the next and previous attributes of the nodes, which takes O1 time complexity. So what kinds of problems occur when working with a linked list? The biggest problem when working with linked lists is setting them up. Linked lists are not immediately accessible in Python and need to be built from scratch. During the building process for this course, I had to go back a couple times and fix bugs within the linked list class. The best way to get around this is practice and having a cheat sheet. Programming is not all about memorizing every detail algorithm in data structure. So now that we have a grasp of what a linked list is and what it can do, I want to have you solve 2 problems. I'm going to walk you through the first problem and the thought process behind solving it. The next problem is all on you. There will be a provided solution, but I want you to set a timer for 20 to 30 minutes. If you can't solve it by then, come back, take a look at my walkthrough of it. If you did, still come back and see if there's any way that you can improve your solution or at least see a different possibility of solving it. The first problem that we're going to be going over is inserting a node in the middle of the linked list. So to set this up, I'm going to scroll up. You didn't see that? The first thing that we're going to do is, of course, have self and data as the parameters inside of our insert middle function. We'll create a new node, and then, of course, do our, if the linked list is empty, we're going to be using that .isEmpty function, right? Instead of the if linked list doesn't have a head, right? That's just another way of going about it. The next thing that we're going to do after this is we are going to, of course, have an else. And we're going to store the size into, well, the size, and then we're going to create the middle, and middle is equal to size. floor 2, and that'll be important in just a minute. Now we can look for the middle. You can find the middle index by taking the size of the linked list and divide it by 2 using floor division. This is especially important when finding the middle. If we had a linked list with a size of 7, half of 7 is 3.5. Because we cannot insert our new node at the 3.5th spot, we floor it to 3. Then we can insert it after the third item, making our new node at spot number 4. If we had a linked list with a size of 6, half of 6 is 3. We would use that same logic before. If we insert the new node after the third item, the new node will be item number 4. And the list size will be now 7, making it the middle node. After we find the middle spot, we can loop until we get the middle value and adjust next and previous hexadecimal addresses to insert the new node. So when we look at this right here, we of course have the middle, and then we have current num is equal to self.head. We've got a pointer right here, and while the pointer doesn't equal the middle, this is going to loop through. So current num is going to be current num.next, and so on. And then all we're doing right here is just inserting the new node after the floor of the middle. And then of course we increment it by 1. Now that you've got that little walkthrough under your belt, I want you to try the problem below. If you're not reading through the markdown file, the problem is not so simple. I want you to find the middle element of a singly linked list in one pass. Now remember, when working with a singly linked list, there's not going to be a previous attribute for our list. It's just going to be data and next. And of course, we won't be keeping track of size as well. So with those constraints in mind, don't keep track of size, don't have a previous. I want you to try to find the middle element of a singly linked list in one pass. So start your timer for 20 minutes, and I will see you when you get back. Are you ready? Well, here it is. This is how you solve it. So I'm going to walk you through it. We don't have any arguments. We're just returning what the value is in the node in the middle. So we have current node is equal to self.head and middle node is equal to self.head. So the key thought process behind solving this problem is having 2 pointers. And every other step in the loop, I want you to increment the middle node, and every step I want you to increment the current node. We're going to have length equal to 0, and every single time we loop, I want the length to increase by 1. And that's really important when we're doing math. So we're going to have while current node.next doesn't equal none, length increments by 1, and then if length modulus 2 equal to 0, this is when we're going to move the middle node to the next node. So we start off with 0, length gets incremented by 1, so length is now equal to 1. Is length modulus 2? Nope, that doesn't pass. So current node is equal to current node.next. All right, length is 2. Is 2 modulus 2 equal to 0? Yes. So we, of course, move the middle node to the next node, and of course the current node to the node after that. And it'll keep going until current node actually hits the end. And when it hits the end, our middle node will actually be on the middle because it's going half as fast, and half of a full is the middle. We have one check actually at the bottom too, because if we have an even number of nodes, it's going to yield us a non-integer number when we do the modulus for it. So what we do here is we have the length. If the length modulus 2 is equal to 1, if the 1 is the remainder, then we can just pop the middle node to the next. And then we just return the middle node.data. So when we scroll down here, if I want to do that, we're going to go, the middle node should be C. So we're going to go print return or we're going to call the linked list first return middle. And when we print that out, I'm sorry, not linked list. We got to do new list. Let me run that one more time. And ta-da! C is the output.